All right, so transport. We have finished our discussion of all four of our macromolecules. We've talked about nucleotides and nucleic acids. We've talked about amino acids and peptides and proteins. We've talked about monosaccharides and carbohydrates and polysaccharides. And then we finished up talking about lipids and specifically triglycerides. So now we're going to sort of put a lot of these pieces together. We talked about phospholipids being used to make lipid membranes. And that's an important piece of either the structural integrity of a prokaryotic cell or sort of the compartmentalization that we get when we have eukaryotic cells in organism or in eukaryotes. And so we want to be able to think about moving things again between these compartments that are separated by these lipid bilayers. And many times these molecules are going to be some of those small pieces that we've been talking about. So to start out this learning unit, we want to think about and bring in some pieces that we've already learned about and talk about the thermodynamics of transport. And very simply, I just want you to think about, we'll get to these equations here in a minute, but when we're talking about transport, we're really talking about the interconversion of some substance A from the outside to the inside, okay? And when we're talking about any simple equation here, what we can think about is, creating an equilibrium constant for that, products over the reactants. And we know when we're talking about thermodynamics, we want to be talking about free energy. Here's an important equation that we know. Delta G equals minus RT ln of KEQ. So I sort of want to put these pieces together here to kind of remind us where we've been and how we're going to be able to think about this. So again, this is our very simple equation. How do we think about moving a molecule A between inside and outside compartments, right? This is sort of the money equation that's going to tell us, the thermodynamics of this process. We can relate it to an equilibrium constant. So there's a direct relationship between the equilibrium constant and the delta G value, right? That equilibrium constant is really products over reactants. So if I'm looking at this simple equation, concentration of A in is the product. That's where I'm going to. Concentration of A on the outside is where I started from. So one last piece to sort of highlight, and I mentioned this already, but when we're highlighting these differences in concentration between the inside and outside, whether we're talking about a cell or a compartment within a cell is basically going to be delineating prokaryotes and eukaryotes. So again, we can talk about differences in concentration of that substance A, both inside and outside. And again, we'll be talking about the inside and the outside of a cell when we're talking about prokaryotes. Okay, and when we're talking about the inside and outside of a compartment, that is going to be referring to eukaryotes, and specifically the organelles that we have within those eukaryotes. And very importantly, a key organelle that we'll spend a lot of time talking about are mitochondria. We're also going to talk about chloroplasts because we are going to learn sort of about some plant biochemistry, but those again, both mitochondria and chloroplasts, we'll learn about why those are ancient bacteria that sort of still live within our cells. That's how eukaryotes were formed, is basically by the sequestration of energy-producing bacteria that then became those important organelles of mitochondria and chloroplasts. Okay, so I want to highlight here another piece that we want to think about is when we're talking about this thermodynamics, right? So highlight here, when we're talking about thermodynamics, we are really talking about free energy. And so what we want to think about is that free energy piece. That delta G really has two parts to it. We've talked about this already, like way in the beginning when we sort of reviewed sort of our thermodynamics. There is a magnitude and there is a sign for delta G. Both are important. Let's first talk about the magnitude piece, okay? And that means the numerical value that we have for delta G. This is going to be directly proportional and related to the force of the gradient. Okay, and what I want you to think about here, we're going to have lots of toy analogies to help us understand things. I want you to think about a slingshot, right? And I've got a slingshot where I'm pulling that rubber band back. I want you to think about how far I pull my rubber band back has to do with the magnitude of delta G. The more that I pull that back, the stronger the force is to have whatever I'm launching from my slingshot be put forward. So that's the magnitude of delta G. That's going to be related to the force of the gradient. Now the sign of delta G is also important, and that has to do with the direction of my spontaneous process. I can't spell right now. Spontaneous process. Remembering always, or I should say movement, because we're talking about moving things, transporting things. We always, again, want to be thinking about the sign being negative for a spontaneous process, okay? So back to my slingshot analogy, let's imagine that this is reactants going over to products, reactants to products, okay? So again, if I've got a slingshot that I'm pulling in this direction and then I'm facing my products, I'm going to be moving towards, and in this case, if I'm talking about the movement of A, it's going to be moving A in. If A is my product, that's going to be, if delta G is negative, that's going to be a spontaneous process to move A in that direction. What we're going to see now is that's going to be talking about delta G's that are negative. That's going to be flowing downhill. Okay, that's going to be taking A from a high concentration to a low. Okay, if I have my slingshot in the opposite direction where I'm having a positive delta G, that is going to be a non-spontaneous process. I'm still can potentially have the same magnitude, but it's going to be an uphill process. And we'll talk about how we can sort of handle those processes of transport when we get to sort of talking about the different types of transport. Okay, the last little piece I want to have here, and then we'll sort of delve into these equations, is highlighting what this little piece is here. Okay, well, let me actually start first with these equations, okay? I know they can look scary, but they're all sort of related to the equation that you guys had to know. Delta G equals minus RT ln of K, right? If we say that our K is equal to this parameter, well, then that is our simple equation, right? Moving something from an inside to, or an outside to an inside compartment. This is basically the same equation showing that movement between compartments, but it's adding an extra bonus feature, if you will, to it. And we don't need to really worry about what all of these pieces are, but it's we've got an effective nuclear charge, we've got Faraday's constant, we've got a delta psi. These are all things that relate to the ability of a charge to contribute to the thermodynamic driving force. So that's all that this really is. This is going to be the effect of moving a charged species. Okay, and that is going to allow us to build up a charge gradient. Okay, so we're going to build up a charge gradient. Now, I will highlight, maybe it's worth kind of mentioning over here, that when we have just the movement of compound A, this is going to be a concentration gradient. Okay, so all of these red terms here refer to concentration gradient, right? That's our concentration gradient. But we can have sort of a bonus extra contribution to our thermodynamic driving force, contributing to the magnitude of that if what we're moving is also charged, okay? And sort of wrapping up this slide here and highlighting some of the differences we're going to see when we consider transport in different sort of systems. When we talk about sort of fuel metabolism and we take fuel and we ultimately harvest the electrons from that, those electrons go to the electron transport chain, and hopefully you're remembering some of this. The purpose of the electron transport chain is to generate a proton gradient. Okay, I'm going to highlight that that process happens in mitochondria in your cells, and it can happen in both mitochondria and chloroplasts in plant cells. So let's talk about why those are similar but different. So mitochondria versus chloroplasts. Okay, and I'm going to highlight here, I'm going to use some color systems that we're going to use frequently. Mitochondria, I'm always going to use blue for when we talk about these organelles. Chloroplasts, I'm going to talk about, and I'll use green. Again, both of these are going to move protons to generate a proton gradient that we can use to synthesize ATP. But I'm going to highlight that mitochondria, when they pump protons, they are going to be able to use the concentration gradient and the charge component. Okay? Chloroplasts, and we'll talk about the details of why, but to give you a little preview, these are only, when they pump their proton gradients, they are only going to be able to use the charge piece of it, and the concentration piece of it. And the reason is there is the free flow of some ions in chloroplasts that will dissipate any charge gradient. You cannot build up a charge gradient in chloroplasts the way that you do in mitochondria. So what that means is that magnitude for mitochondria can be bigger because you have both charge and concentration contributions. So let's actually go and highlight and put some color in here. The charge contribution plus the concentration distribution or contribution. And then for chloroplasts, it's only the concentration contribution. So what that means is for chloroplasts to use a proton gradient and synthesize ATP, they actually have to have a greater concentration gradient of protons, a greater difference in pH to achieve the same ATP production. So I know that there was a lot on this slide, but hopefully tying some pieces together from things that we've already talked about to understand the thermodynamics of transport.